energy transfer. Okay, I often like to call it heat transfer. So you think of energy, you think of heat. But here we go. So this diagram is very typical science class diagram of three different types of energy being transferred here. What you have is A is convection. It's trying to show, there's a flame here. It's trying to show the water in the pot moving. Conduction is if you touch the handle with, in this case, a pot holder hand. And radiation is these given off in the form of waves. So if you stand near a fire and you can like feel the heat coming off, that's usually radiation. So let's get into these. So conduction, physically touching something, direct atom to atom transfer. So I have this hot cup of coffee here, right? And I'm touching it and I feel it to be warm. Okay, so it's transferring heat to my hand. That is direct because I'm touching the mug, which is hot. So that's one example of it. This is actually a diagram from a Regents exam. I don't love it, but this is how they presented it. Where the flame, this is a metal rod, the flame is touching the rod, so there's touching there, and then that causes the atoms in the rod to vibrate faster. It's giving energy to the atoms and vibrate faster, and that's basically what heating something up is. It's the increase in temperature of the atoms and it vibrate faster, which is pretty cool to think about. Which is why something expands. When you heat it up, the atoms hit each other faster and harder, and therefore it transfers more energy. It causes it to expand a little bit. So that's cool. Radiation. The best example is energy from the sun. Sunlight is a form of radiation. Energy in the form of waves. Let's give another example of it is microwave oven. Okay, turn on a microwave. It uses a specific type of electromagnetic energy called microwaves to heat the food, or heat the water in the food, really. But you can't see the waves themselves. They're invisible. And this is on your reference table. Reference table, page 14. If you can see this. Page 14 at the bottom, they have it's this chart, electromagnetic spectrum. Okay, and they show some things here. Okay, so here you go. It shows visible light. I put the colors in there. I like that. It shows violet to red. The visible light spectrum is here. So there's a lot of electromagnetic radiation. Our eyes have evolved to only be able to see this. So you've heard of X-rays. You can't see X-rays through the air. You can't see microwaves. You can't see radio waves in the air. They're there, but our eyes can't detect them. And these are smaller wavelengths, says decreasing wavelength. These are longer wavelengths. So I put them in there to give you a sense. Now these wavelengths is really small, you can't see them, but so they're longer wavelength here, okay, smaller wavelength here, and the smallest are here. So this is all radiation, energy in the form of radiation. Convection is our third type of energy transfer, and in this case it usually it will involve some sort of fluid, something that can move, really a gas or a liquid. So in this case it is a beaker of water, it has a Bunsen burner, and they have a colored dye pellet. And basically it asks, so this is going to dissolve and color the water, and how will the water move, or the colored water move? And the answer is like this. It's going to be heated and rise like this, and then move around this way. So this is what convection is, or it's called a convection current. Let's have some other examples of it. I like this one. This is also showing convection. You have a radiator in the wintertime that heats a room, that basically it gets really hot, and then the air touches it. The air gets hotter. It will expand because it to be less dense, and that causes it to rise. So the hot air rises and moves along the ceiling. This diagram has a cold window here. So here, the air touching this is cooling. Cold air becomes, cool air is more dense, so then that will sink to the ground, and then it gets pulled back this way. And this is how that heat gets transferred within that room. Here's another example of it. This is another classic science class thing, where it's this box here with the candle and a glass front, these glass tubes, and what happens is it heats the air in here, the air rises out this way, and then it pulls in more air here. So this, I believe, was a multiple choice question. How will the air move within this chamber? And it goes, this air will rise here and it goes in this general direction. So this is an example of convection, one that you can often do in a classroom, though it never really works that great for me, but you may have seen it. Hopefully your teacher got it to be able to work really well. Here is, this was a question on a Regents exam, and So I had a Bunsen burner in the middle. It says there's convection currents here. Draw in the arrowheads of how this would be moving. So this is the heat sources right here. So it would look like this, okay? So here you have the hot water moving here, and then it does this. The difficulty here is that this is all stuff you usually can't see. You can't see the water in a pot moving. You can't see the air in a room moving. So that's really the difficult part for convection for a lot of people. So just to review, because this stuff is important, just in general, it's important. Conduction involves touching, physical contact, heat being transferred that way. Convection, movement in a fluid like a liquid or a gas, and caused by density differences. And radiation, energy in the form of waves. Sunlight is a good example. Microwaves are a good example too. So, know it. I'm calling this heat transfer on Earth. Let's do it. So, basic one, sun giving energy to the Earth. Sunlight is called insolation. As a matter of fact, I want to draw it more like this because it's just radiation. So I like to show the waves there to make it look a little more understandable. And this is called insulation with an O, not insulation with a U is the pink stuff that's in the walls in your attic and stuff. But insolation is sunlight. Now, it's short for incoming solar radiation. That's where it comes from. So know that. Insolation. The word comes up a lot. It means sunlight. So here's just a quick thing on that. Which will reflect the most insolation? Okay, so there's two things that matter here, color and texture. The answer here is going to be A, because it's light color and smooth texture. Smooth surfaces reflect more and absorb less. So the next question is, of these same materials, which will absorb the most insolation? And you probably know that dark colors are going to absorb more sunlight, but it's also the rough texture. Dark color, rough texture are necessary for absorbing more radiation, in this case insolation, meaning sunlight. Know it. And here's the question for an example. Equal areas of which surface would absorb the greatest amount of insolation on a sunny day? Keyword being absorb. Therefore, we're looking at dark colored rough surface. Okay? This is another Regents question, and it shows sunlight coming in and showing the amount being reflected. You see the arrow coming off. So, and our materials are sand, a grassy field, fresh snow, and a forest. Well, which is reflecting the most? Fresh snow, pretty smooth surface and really white, so it reflects a lot and it has percentages here. Which will absorb the most and therefore reflect the least is the forest. Think of a forest being dark color, really rough texture if you think of the tops of the trees. So that's a good example from a Regents exam. That diagram is used. So this is getting a little more complicated. So basically the sun, the energy from the sun is this short wave, if you could see the waves. Not to scale, by the way, but this short wave radiation, it gets absorbed by the Earth, and then the Earth gives off this longer wave radiation. Air doesn't really absorb a lot of sunlight by the nature of its wavelength of the sunlight. Air is not a good absorber of sunlight, but Earth gets warm and it gives off this, which is infrared radiation, okay, which we're going to get to and how that warms Earth. Check this out. So infrared, we see infrared, this is on page 14 of the reference table, that's where you see infrared, though this diagram usually does not help you answer the questions where I'm going with this, which is global warming. So here's another example from the Regents exam. It shows visible light coming in a window. It heats up the table, and the table gives off infrared radiation in this case. So here is this stuff comes up a lot. Most of the long wave energy radiated from Earth and lost to space on a cloudless night is infrared. Infrared, okay, that's what Earth gives off. Now, this is the greenhouse effect. I am sure you've heard of the greenhouse effect at some point. Now, this is how it gets its name. Okay, so a greenhouse works like this. If you know a greenhouse, it is basically a glass building where you grow plants. This helps it be warm so you can grow plants in the cooler weather. So solar radiation comes in. Notice it's shorter wavelength. It heats the ground and the plants or anything that's inside the greenhouse. And that stuff all gives off radiation, which is infrared, longer wavelength. And the idea here is that this type of radiation goes through the glass, but this cannot go through the glass, okay? And that causes the air inside the greenhouse to warm. Now, in our environment, the greenhouse effect, when we talk about our climate, is it's not glass that keeps this energy in. It is greenhouse gases will absorb this infrared radiation. Okay, and the greenhouse gases are, these are the three main ones that you need to know: carbon dioxide, CO2, methane, CH4, and water vapor. Know those, it's important, okay? And this is a big issue in the future, so everyone really wants you and your generation to know this. So basically it goes like this. These three greenhouse gases are increased by burning fossil fuels and deforestation, or at least definitely carbon dioxide is increased by burning fossil fuels and deforestation. And this causes climate change, which is warming, because if we go back here, what's absorbing this are the greenhouse gases. You have more greenhouse gases in the atmosphere, there's more absorption, hence warming. So this is all important to know and understand, because there's a lot of different types of questions that involve you understanding them all to get them right. So here's an example of one. In addition to carbon dioxide, two other major greenhouse gases in Earth's atmosphere are water vapor and methane. That's an example of one. Here's an example of another one. It says identify one major greenhouse gas other than carbon dioxide. I think for so long, kids just knew carbon dioxide, but they didn't know any other one. So they do stuff like this. So make sure you know those three, because I've seen questions that even ask for all three in multiple choice. So know them. And just to review, they are this: carbon dioxide, methane, and water vapor are the greenhouse gases. Water and energy. Now, this is a pretty obscure part of the reference table. It's on page 1. It's like right in the middle of page 1, and it looks like this. Okay, properties of water. I'm gonna, not the most exciting part, geez. It's not, but it's on there. So we've seen more and more questions on the Regents exam using this chart. It was always the most obscure one, but basically it talks about how much heat energy is gained or lost during phase changes. Now, I know it's all joules per gram. You don't know what joules are. I'm not going to explain what joules are, but it's a measurement of basically of heat in this case. So, and if you notice anything, this is all like the solid to liquid going either way. There's less here. This is all vapor to liquid, and either way, whether it's gained or lost, and it's much more. So that's important. But this is some of the questions you may see. During which phase change does water release the most heat energy? Release the most heat energy, the most, and then look at the choices here. Where does it release the most? And you gotta look around. So it's going to be this one: condensation. Oh yeah, released. That's key. So look for that. Condensation is the answer, looking up the chart. So just know that it's on the chart. They don't expect you to have this memorized. Which process of the water cycle occurs when water absorbs 2,260 joules of heat energy per gram? Well, you got to look here. Absorbs. Now, it doesn't say the word absorb, so you got to like be able to apply this here and realize that it's gained. The water gains that energy, that much of it, during the process of vaporization. Not a choice. You have to know vaporization and evaporation are the same thing. So that's one of those maybe a harder question, depending on your knowledge of vocabulary, but there you go, properties of water. Seasons and Earth's orbit. This is a big topic. There are questions on this every single test, so make sure you're on top of it. So what this is showing is Earth's orbit around the sun, not to scale by any means, but it basically to go from C, all from D to A to B back to C takes 1 year. So notice here, the Earth's axis is tilted. We're going to call the North Pole tilted like to the left in this case, okay? And it's always tilted the same direction. That tilt doesn't change. This diagram here shows a different view of the same thing, but basically the tilt now is this way. So don't always think left or right. Just think about, is the North Pole tilted towards the sun or away from the sun? Towards the sun, away from the sun. That is going to be essential for this. So First thing I want to point out is if this is Earth's orbital plane here, Earth's axis is tilted. It's not straight up and down. And that tilt is 23.5 degrees of, that's what the angle is. That's important to know, 23.5 degrees. And that tilt of the axis affects the angle that the sun hits at any location. Okay, that's important. This is kind of shown here. So this is like, let's say they take sunlight and make it into like a flashlight beam here. So here's directly overhead, a 90-degree angle. Here it's 66.5, and here that angle is 43. The key thing here, it may not be that obvious on this picture, but it is true. Here, that light is more concentrated here. It's all in one area. The lower the angle, the more spread out this area gets larger. Same amount of heat, larger area, larger area. Okay, this is called the angle of insolation. Insolation means sunlight. So the angle of insolation hidden in area. Okay, and so this will have the most intense insolation because the angle is the highest, directly overhead. The sun is strongest. That is important. This diagram here is zoomed in of the Earth, what the Earth looks like during the winter time. What I want to point out, the North Pole tilted away from the sun. Okay, winter, North Pole tilted away from the sun. That's important to know. I want to point out, when I say winter, I mean winter for us in the US, because as a winter for us, it is summer for the people in the southern hemisphere. Okay, now let's point out why that is. So let's say you are in the southern hemisphere. Let's say you're right here in the southern hemisphere. Okay, notice where the sun is. The sun rays kind of directly overhead. So what would the intensity look like? Well, that would be like this. Okay, and that's as concentrated as the sun can get. So the sun's directly overhead. So that's why it's really warm for them. As opposed to where we are, let's say we're like this, we're up here. Well, if that's directly overhead, the sun is coming in at much more of an angle. This would be at noon. So it would be more like this. Okay, we're here. As a matter of fact, in the wintertime, the sun is even lower in the sky. At noon, it's like 24 degrees. So it's even lower angle. And it's that angle, the intensity of the sunlight, that causes these seasons. So that is important to know. Now, this diagram here shows orientation of summer. Now it changed. Now the sun's coming this way. So you have the North Pole tilted towards the sun. So, okay, that is key. Make sure that you know this, commit it to memory. So now where this person in the southern hemisphere who had just had the sun directly overhead before, well, they may be about here now, and notice, well, that's overhead for them. The sun's lower in the sky. Okay, so that'd be winter for them. And where we are, we would be something like this in New York, like this. Now notice, the sun's not directly overhead. The sun is never directly overhead in New York. It's never 90 degrees up. Make sure you know that. The highest it could get is 72 degrees above the horizon. But it is higher, therefore the sun is stronger, therefore it's summer. Important concept. Okay, now we'll go back to here. So in this diagram here, showing North Pole tilted away from the sun, it's winter. North Pole tilted towards the sun, it is summer for us in the state of New York. And then here, just a different diagram, kind of looking at it from a different perspective. In this case, the North Pole tilted towards the sun, summer, and then this would be winter as the North Pole is tilted away. What I also want to point out, look, you're at the North Pole right here, and Earth is rotating once every day. Do you ever rotate into this dark nighttime? You don't. Okay, so if you're very close to the North Pole in the Arctic Circle in the summertime, that's where they have 24 hours of sunlight. All right, this is totally cool. And at that same time, if you're down in the South Pole, you have 24 hours of darkness. Reverse, when it's winter time for us, look, they never rotate into the light side, so they have 24 hours of darkness. Sad face, that would stink. And then the South Pole has 24 hours of light then, so that's totally cool. I do want to say this, be careful, because seasons are not about how close we are to the sun. Summer is not when we're closest to the sun. This is summer. Look, the axis tilted towards the sun. We are actually 5 million miles, in this 5 million miles, kilometers further away in the summer. We're further away in the summer. We're closer in the winter, but it's all about the tilt because it's all about the angle of insolation. I can't get that into your head enough. All right, so summer and winter, all again based on the axis. Know it. the shadow created by the sun. Check this out. So what we have here, surface of Earth, here's an observer, and this shows the sun's path. Now, obviously, this is not the sky. It's trying to represent the sky, I guess. And it shows the sun's path during the day, this case July 21st, and as the sun rises here, the sun moves throughout the morning like this. Solar noon is here, and then sunset is over here. And notice that in this case, we're looking at it like this. North is this way, south is this way. And another perspective to look at it is like this, where they kind of swapped it around. Now, south is this way, I'm sorry. North is over there, and this is a different day. And we'll get into that. What I want to focus on is the shadow that is created by the sun. And so to do that, what I did was I got my flashlight and I got Pirate Guy here, and we filmed some quick videos just to show how it works. Check it out. The relationship between the height of the sun in the sky and shadow is important. So what I have here is a flashlight and this dude, this like Pirate Guy, okay? And I'm going to show how this works. So this is going to represent the sun, this flashlight here. So when the sun is low, look how long the shadow of Pirate Guy is. And as I bring this higher in the sky, the sun's higher in the sky, higher, 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 his shadow gets shorter, shorter, shorter. And then when it's directly overhead, he basically has no shadow. Okay, and then when I bring it back down, again, the lower in the sky, the lower the angle, the longer his shadow gets. And then basically at like sunrise or sunset, the shadow gets almost infinitely long. So now, Pirate Guy and our flashlight are going to help us see what the shadow would look like during the course of a day. Okay, so we're going to stand Pirate Guy up. Notice the compass rose right there. And we're going to start like right here, sunrise. Okay, so now look at the length of the shadow. Sun is rising, sun's rising, rising through the morning, rising through the morning. And then that would be noon right there. I'm going to pause it. Okay, so at noon, notice the shadow is shortest for the day because the sun is highest in the sky and the shadow points due north. Okay, now I'm going to continue to play. Okay, it goes past noon and the sun starts to be going down, and the shadow gets longer and longer and longer and longer and longer, and then we're basically at sunset. Thanks, Pirate Guy. Okay, those are pretty cool. I think they show it well. What I'm going to do now is kind of show it in the real world. This is a video that I filmed in my driveway in the summer of 2012. What were you doing in the summer of 2012? Well, I know what I was doing when I was filming this video, but it does really show how the sun moves throughout a good chunk of the day. So let's watch that now. All right, I think those videos really show it. This is a tough topic, and doing things like that, you know, watch them again if you need to really get it into your brain to understand it, because you experience the sun every single day, but it's still really hard. So this is hard, but it's very you can learn it. You just got to really put your time in. So for instance, this is a type of question that you may get. Look at that length of shadow. So this would be short shadow, long shadow at really throughout from sunrise to sunset, and this is solar noon. I think this was a multiple choice question. The correct choice looks like this. Okay, it is shortest shadow at solar noon and longest at sunrise and sunset. And hopefully those videos that I filmed with my friend Pirate Guy really helped. So here's the question here, where you have A, B, C, D. At which location of the sun would the shadow of the observer be the longest? I'll let you think about it for a second, but the answer is going to be D, right? The lower in the sky, the longer the shadow. This is a multiple choice question, and hopefully if you know that, it will be a pretty straightforward question for you. This one is what direction is the man facing? And the key part is that you're told this, it represents noon or solar noon in New York State. See his shadow and see the tree. So hopefully you recognize this, and this is a big one. It's north. At solar noon, the shadow of the sun points due north, okay? So make sure you know it. Here's another one. So we have always look at what you're looking at here. You have different, we have just labeled June 21st and December 21st. So at noon of which of these 2 days will the man's shadow be the shortest? Okay, shortest shadow. So you really got to think about it. So this here would be the shadow on December 21st. I kind of represented his shadow, length of his shadow, okay, because it's lower in the sky. And on June 21st, it would be like this. It would be shorter because the sun is higher in the sky at solar noon. Therefore, he will have the shortest shadow on June 21st. This stuff's important. Make sure you know it. Sun's path. This diagram is trying to represent the sun's path during, in this case, these actually 4 different days, because these are the same path, okay? Always want to look at the north, south, east, and west and sort of get bearings of what is going on here. So, some things I want to point out. These all represent sunrise locations. The sun always rises somewhere in the east, okay? Not directly east, only 2 days a year is directly east. We call this anything over here south of due east. We all call this north of due east. And those are just those 3 days. So for instance, in mid-August, the sunrise would be somewhere around here, just to give you a sense of what this is showing. So understanding this is really important. This represents the horizon for that person. So recognize that too. And then these are sunset locations because they always set somewhere towards the west. This would be sunset in the north of due west. And that is the phrase we use, north of due west. So hopefully that is just review for you. Now, this is where it gets challenging for kids. So this is the path in New York State. It really matters where you are, but in New York on December 21st, this gives you an idea of what the path is like. So it rises south of due east. It sets south of due west. The sunlight hours is 9 hours of sunlight, about 9 hours, okay? Because the sun appears to move along this path at 15 degrees every hour. The sun's movement along this path is the same all the time because that's based on Earth's rotation. So the shorter the path is, the shorter the daylight hours, okay? And the angle of insolation at solar noon is 24 degrees above the horizon for that guy. It's kind of shown on here. Also, December 21st is the first day of winter. It's called the winter solstice. There's a lot here. You need to really know this and commit it to memory. You may need to watch this video a few times. And I want to point out the angle of insolation at solar noon on this day, 24 degrees above the horizon. You should know that as well. Sometimes you have to draw that in, okay? So that can be tricky if you don't know it. On June 21st, this is the path on June 21st. So it's called the summer solstice. It's the first day of summer. It rises here, north of due east. The sun sets over here, north of due west. We have about 15 hours of sunlight, again, because this is a much longer path, and the sun travels 15 degrees of arc every hour, so we get about 15 hours of sunlight. And the angle of insolation at solar noon is 72 degrees. Notice, it is never directly overhead in New York State. You may feel like it is, but it never is. Okay, so don't get tricked on that one. And so, for instance, I drew this in 72-degree angle is the angle of insolation on this day. So commit that to memory as well. I'll show a way that's going to help you with that. So, and then March 21st and September 23rd, these are the equinoxes, okay, the spring equinox and fall equinox. And these are the only 2 days of the year where the sun rises directly east, we call it due east, and it sets due west. Okay, that's key. These sunlight hours, 12 hours. In equinoxes, equal amount of sunlight and darkness. Actually, the whole, everywhere on Earth gets 12 hours. So it's all equal across Earth, which is kind of cool. And the angle of insolation at solar noon in New York State is 48 degrees above the horizon. Okay, and I have a diagram for that as well. So angle of insolation on this day is 48 degrees. This is a lot to memorize, but you do need to memorize it. Okay, So this is sort of showing it, all of these angles here, 24 degrees, 48, 72. Now, how are you going to memorize that? Well, here's the tip. Just remember 24. If you remember 24, check this out. It's 24, you start with 24, you add 24 to it, you get 48, and you add 24 to that, and you get 72. So that tip I found really helps students. So go through this again, make sure you know it, because I can never guarantee anything, but if there will be a question on this test. If there's not a question on this, on the Regents exam, I'll eat my hat. Know it.